So welcome to our video talking about the ideal gas law. This is really meant to accompany the questions that you have in D2L, so make sure that you're looking at both of those together. There'll be places where you're asked to pause the video so that you can then do a couple of those questions and then you'll get some feedback on it. So as we're looking at the ideal gas law, we really want to remember where we started. So in our last class, we were talking about kinetic molecular theory and how molecules of gases would move. And we had this idea that gases are really composed of these molecules. They move in a straight line, right? They bounce off other molecules when they collide that can transfer energy between them. And then they also hit the walls of the container and will bounce off those things. And in our discussion of that, there were a couple assumptions that we had. One of the assumptions was that the size of the gas particle was negligibly small. It's just these little teeny things bouncing around. They don't really take up any space. We also then talked about how the average kinetic energy of the particles was related to the temperature, right? We saw as we increased the temperature, that meant there was more kinetic energy, so the molecules were moving faster, moving more, therefore having more collisions and stuff like that. We also talked about the fact that the pressure of a gas really comes from the collisions of those gas particles with the wall, right? So hitting the wall was essentially pushing it out. That's what causes gas pressure. And we also had the one other assumption that there were really no attractive or repulsive forces, for that matter, between the particles. So when we talked about intermolecular forces, we talked about how things would be attracted. Well, when we talk about gases, we really say, yep, there aren't any of those. When we're talking about when we talked about our gases the other day, in our ideal gas situation, none of those things happen. So all of our collisions are completely elastic. There's no energy that's lost. The particles don't stick together and stuff like that. And what we found is that the particles, some of the properties of the gas, pressure and volume in particular, didn't depend on the type of the particles, just the number of particles that we had. And so those were some of the things that we saw from that last assignment that we had. So just a couple of things to kind of get us rolling here. First of all, I want you to think about, well, what happens to the air pressure as we would go up a mountain? Okay, so what are the options there? And then think about and provide an answer for why. So let me give you a moment to pause the video. Again, if you don't have D2L open already, go in there, open up the accompanying assignment, pre-class activity, and start answering these questions. So answer the multiple choice, give the explanation for why. Okay, so hopefully you've had a chance now to answer that on D2L. So if we think about what's going on here, right? The air pressure that we experience is really the weight of all those molecules that we have in the entire air column, right? So if you're down here, near the ground, right, you have this very large column of air that's pushing down and creating that pressure, contributing to it. If you go up a mountain, right, so let's say you're up here, there's just simply less air at a higher elevation that's pushing down. And so as we go up, we actually would expect our air pressure to go down because there's, again, just fewer molecules that are providing that pressure. Okay, so now let's see if we can take that same sort of idea and do a little bit more with it. So let's imagine that we have a rubber balloon and it's filled with air, and we take it and we pull it down into a lake. So what's going to happen to the density of the air in the balloon? Okay, so again, we've got the answers of increase, decrease stays the same. And then I want you to give an answer why. So really think about, why does that happen? So again, pause the video, answer those questions on D2L. Once you get those done, restart this. Okay, so hopefully you've had a chance to answer those questions on D2L. Okay, so we think about our balloon, right? That we've got our balloon, there are these molecules that are sitting in here. Again, of course, they're not this large, but it gives us a good visual representation just to kind of help understand what's going on here, right? And these things would be moving around. They're hitting the edge of that balloon. They're pushing it out. But at the same time, we've got air outside, right? And that's pushing in. And so the collisions with the outside of the balloon are going to be pushing those things in, right? And we get to an equilibrium where these two things, there's the same amount of pressure on both sides, and the balloon is inflated to that level. Okay, if we take this thing and we pull it down, and we put it in the bottom of the lake, right, what we're going to do is we're going to increase the number of collisions on the outside surface of that balloon, right? There's just a lot more water molecules. Those are much more densely packed, and so there's going to be more collisions. That's going to increase the amount of pressure, or we can think about the total weight that's pushing down on it is much larger. And so what that's going to do is it's going to shrink this thing down, right? So we're going to see that we should have a decrease in terms of the total volume. Now, of course, if we still have the same mass and we decrease the volume, this was actually asking us about density, right? So if we decrease the volume, mass is the same, the density itself should actually go up. Okay, so let's do another test and just kind of make sure we're trying to understand things here. So the figure below that we have down here represents two different gases. We have helium and oxygen, they're at the same temperature. And what we want you to identify is which of these two gases is A. Is it helium or is it oxygen? Or can you not tell? Okay. And of course, then make sure that you can explain how you made your decision. Okay. That's often what we're really interested in. So take a moment, pause the video, again, answer the questions on D2L, restart this once you have that done. Okay, so hopefully you've had a chance to answer those questions. And so now if we look at this, we need to think about what's going on. And so what you saw in the simulation the other day, right, is that the heavier molecules tended to move slower, right? Because we have the same amount of kinetic energy that's present. But we had that kinetic energy equals 1/2 mv squared. And so if the mass is higher, the velocity has to be slower. And so we look at this and we go, okay, well, hey, it's moving slower on average, right? There's a distribution of speeds that we have going on, but the average, again, is probably relatively close to this peak here. And so we see that gas A on average is moving slower, which is going to tell us it's the heavier of the two. And so that would be oxygen in this particular case. Okay, so we're kind of, again, touching on some of the stuff that we've already talked about. Make sure that we feel pretty comfortable with that. Now, we're going to be talking about essentially the ideal gas law. And so under normal temperatures and pressures, we often assume that gases behave ideally. And I already mentioned what the assumptions are. The assumptions are that the volume occupied by the gas is actually really small. And the other aspect is that there are no intermolecular forces. So there's no attractive or repulsive forces in any way that's impacting the particles and how they interact. So those are our assumptions. And so if those things hold true, there's some mathematical relationships that come out of this. And we saw these in the simulation that you were using the other day. So what we saw is volume and pressure had a inverse relationship, right? When we increased pressure, volume went down. When volume went down, or when volume went up, pressure went down. And so again, there's an inverse relationship. And we can represent that mathematically as the pressure times the volume equals a constant. Okay? We also saw a relationship between volume and temperature, right? And here what we saw is there was a direct relationship that the volume itself was proportional to the temperature. So if we increase the temperature, the volume went up. If we decrease the temperature, the volume went down. The way that we can represent that mathematically is, well, the volume divided by the temperature is now going to be equal to a constant. Now, one of the things that's really important here, we've got this note, is we always need to make sure that the temperature is actually in Kelvin when we do this. Okay. The reason being, we need to have a scale where 0 is the bottom of the temperature scale. So if we think about something like Celsius, right, we can have negative values of Celsius in terms of the temperature. But obviously, we couldn't put a negative value in here because that would give us a negative volume, and that isn't something that makes sense. So we need a temperature scale where 0 degrees or 0 of that scale is absolute 0. And so that is Kelvin in this particular case. So we always want to make sure when we're doing these kinds of pieces that we're using Kelvin. There's also a relationship between the number of particles and the volume. And you saw this as well the other day, that again, there was a direct relationship between volume and number of particles. And so we can again represent that as V over N is going to be equal to a constant. So if we take all those things and we put them together, what we see is that, you know, volume is going to be proportional, inversely proportional to pressure and directly proportional to temperature and volume. So essentially we can combine all these pieces over here, and what we get is PV over NT is going to be equal to some constant. And in chemistry, we call that constant the ideal gas constant. We give it the letter R. And so there's a good chance if you've seen this before in a class, you may have seen, you know, kind of this relationship, PV equals over nRT equals R, or more commonly, it's actually written PV equals nRT. So PIVNRT, for those of you guys who may have heard that. And R can actually be determined experimentally. It's 0.08221 or 82057 is a little bit more accurate, but again, often this works quite well. And so we can then use this relationship to make really good approximations for doing calculations and stuff like that to understand the relationship between pressure, volume, moles, and temperature. So let's see if we can take that out for a little bit of a spin. So let's imagine that you're a scuba diver, you're on the surface of the water, and you're breathing. The air that you're breathing is at 1 atmosphere, right? Because that's typically what we experience just in the world. That's how we define an atmosphere. It's the pressure on average at sea level. And if the temperature is 25 degrees Celsius and the person's lung capacity is 6 liters, so how many gas particles would actually be in your lungs? So this is something we should be able to calculate. So let's have you take a few moments and actually try to do that calculation. You've got all the information here. One of the things I'm going to remind you is just write out your units. It's always really helpful to do that. So go into D2L, put your answer in there once you've calculated it, and then restart the video. Okay, hopefully you've had a chance to answer that question, kind of go through that math process, and let's just kind of look at it. So again, we've got that equation, PV equals nRT. So we can rearrange this. Personally, I find it really helpful to sort of rearrange things before I start plugging everything in. It's often an easier time to do it. So we get PV over RT equals N. Just always double check, make sure you have it the right way. Some students will sometimes flip those things. Then we put our R values in. As you can see here, I actually wrote out the units here, and so that helped me realize that, yep, I definitely need to do this conversion. I need to convert over to get to Kelvin, because otherwise my units aren't going to cancel out. And so we're going to find that we have 0.25 moles of gas particles in that particular case. So again, we can see the relationships on how we calculate these things. Now let's imagine that you go down to a depth of 9.14 meters. And when we do that, the pressure is going to increase, right? Just like the balloon that we saw earlier, we're going to have that weight of the water pushing down. So the atmosphere, or the pressure is now going to be two atmospheres. So if we assume that the temperature of the gas is still 25 degrees because it's in a person's body, the lung capacity probably doesn't change. So now how many moles of gas particles would be in the person's lung? So let's have you figure that out. And as you're doing that, I also want you to think about this and answer this question as well. So if the diver is to hold her breath and swim to the surface, and the external pressure goes back to 1 atmosphere, so what would happen to the volume of her lungs and why? Okay, so pause that, take a few moments, answer it on D2L, come back and we'll talk about it in just a moment. Okay, hopefully you've had the chance now to answer that on D2L. And so what we find when we do this calculation, if you do it again, you plug everything in, we're going to get a value of 0.49 moles. And if you think about that, we were at 0.25, so we're at 0.49, so we basically doubled it. In actuality, we really have doubled it because we had a starting pressure of 1 atmosphere before, and now it's 2. So the rest of the calculation is the same. You go from 0.25 to 0.49, just simply because those are rounding issues. And so we'll sometimes see that. But again, if we consider our significant figures, we've doubled it, exactly. And so, cool, we see that relationship, and that's really helpful. And then we can think about, well, what's going to happen if the swimmer comes up to the surface? Well, when we do that, what we're going to do is we're going to do that same sort of equation, PV equals nRT again. Again, this time we'd be solving for volume. And so we put the N, the R, the T, and the P in there, and we're going to get a volume of 12. Now, you might have also been able to just do this to some extent in your head, right? To start to see some of these relationships that exist. Because if we were paying attention, right, we started over here at 6 liters and 2 atmospheres of pressure. Now we went down to 1 atmosphere. And so if we're going to hold temperature, we're going to hold moles the same, then we can go, oh, well, obviously then we're going to have to double that volume. And so again, we see that come out nicely here, that we get 12 liters instead of 6. Obviously, this is a really bad thing for a scuba diver, right? Because your lungs don't have the ability to actually swell up to be twice their volume of their capacity. And so in that case, that tends to end very poorly for the diver. So, you know, one of the things when diving is you have to be careful. You breathe out. There are other things that you can do to surface a little bit more slowly to make sure that you don't get injured from these kinds of things. So that gives you hopefully a sense, and we're going to be able to run and hopefully do a bit of the calculations, really understand quantitatively that relationship between pressure, volume, moles, and temperature. Now, I do want to just take a couple moments and talk a little bit about some of the deviations from the ideal gas law. We're not going to do calculations with this, but I think it's worth just sort of mentioning so you have a little bit of a sense. So the two places where we have these deviations that really become important is if we are at high pressure or if we're at low temperature. That's when it arises. And we can understand why that is, and that's the piece that we're more interested in. So if we're at relatively low pressure, right, we just have a few molecules in this large space. The molecules are pretty small. And so if we take all those molecules, we just kind of shove them in a corner to see how much space they occupy, right? They just occupy this little teeny corner, you know, maybe a couple % worth of the total volume. And so when we put that volume of the container in there, you know, it's essentially negligible how much volume those individual particles are taking up. Now, if we're really high pressures, though, right, we have a lot more molecules given the volume. And what we'd see is, you know, if we took the same number and we kind of just increase the pressure by cutting down the volume, well, all of a sudden that volume that's occupied by those particles becomes a much higher percentage. And when it becomes that much higher percentage, all of a sudden, the maybe 10% or 15% or 20% of the space that they're occupying all of a sudden becomes really important in terms of the calculation. And so there are ways that you can account for this. There's a slightly different version that one uses of the gas law in order to be able to account for it. Again, we're not going to focus on the calculation, but it's good to understand where that comes from. The other place is if we're at low temperatures. And at low temperatures, what ends up happening is, again, in our ideal gas, these molecules are bouncing around. There's absolutely no intermolecular forces. However, if we have a real gas, we know that there are going to be some intermolecular forces, that those slow-moving molecules just barely moving past each other, the intermolecular forces are going to pull them together. And now all of a sudden, instead of having, two particles, they're going to stick together, and those two particles are going to move as one. And remember, the pressure or the volume is really dependent on the number of particles that we have. So if they start sticking together or if they start sticking to the wall, that decreases the effective number of the particles that are present. And when that happens, obviously that's going to alter the results that we would get. And so when we have low temperatures, typically we actually will over-calculate, right? The actual pressure is going to be a little bit lower than we would calculate otherwise. So again, that gives you a little bit of a sense of how we might deviate from the ideal gas law and why that would happen. And again, that's sort of what we're looking for, not the calculations behind it. So then what I'll ask you to do is just complete the rest of the practice questions on D2L, and that should give you a really good understanding for how to do a lot of these kinds of quantitative and use the ideal gas law quantitatively.